One last example to take a look at. Let's check it out. This is a good one. This one is challenging. Water is being pumped into a trough at 2 feet cubed per minute. We see the trough there, see water pouring in. It's this triangular looking trough. We can see all the dimensions. It's 5 feet tall from bottom to top. It's 3 feet wide at the top, and it's 12 feet, like the width or the length, I guess would be better, is 12 feet. And then, we have some water in there, and we can label the depth of the water as H, since that depth is changing over time. Okay. So a couple of questions. First one, how fast is the water level rising when the depth is 1 foot? At the moment the depth is 1 foot, how fast is the water level to the bottom of the trough rising? You kind of think about that, right? As water pours in, right, because of the shape, the water level is going to rise really quickly at first when it's very narrow. But as it gets closer to the top and it's wider, then the water level, if it's always pumping in at the same rate, then the water level is going to be rising slower toward the top of that trough. Then part B, if the water is rising at 3/8 feet per minute, when the depth is 2 feet, how fast is water being pumped? I think that's supposed to say into the trough. Why not? Okay, let's check it out. Obviously, we'll do this one at a time. It's going to take us a long time to answer part A for something like this. So let's get to it. Here we go. I've tried to recreate our image here. Water is being pumped in at 2 feet cubed per minute. We see the trough there. So, right, it's 5 feet tall. It's 3 feet wide here. It's 12 feet long, and then the depth of the water at any given moment, we're just going to say H. How fast is the water level rising when the depth is 1 foot? Now, one thing is kind of nice about this question is they already give us the drawing. The drawing is already labeled with all of the fixed values. It's even got the variable value for the depth of water that's changing. Looking pretty good. But you notice that there is only one variable involved here. The reality is there are two variables, but we really can't label the third variable in the drawing. When we're asking, right, how fast is the water level rising, we'll need to set up an equation. It needs to have more than one variable in it that is changing. Well, what is the other thing that's changing, right? The depth or the height of the water is changing, but something else, right? They tell us that water is being pumped in at 2 feet cubed per minute. That tells us the volume of the water is changing. So let's go down here. What are the changing quantities? Turns out there's two. There's the volume. Let's be real clear. The volume of water, we're going to call that V. And there's the depth, or you might say the height of the water. We're going to call that H. So the first thing we want to do, we got the drawing already. We want an equation relating V and H, an equation that contains both the volume and the height of the water. Turns out this is gonna take some thought, right? How are we gonna do this? We got this three-dimensional thing, right? We can't just jump right to a formula or something. We actually have to piece this together ourselves. Here's what we wanna do. I'm going to recreate just the front of this trough, that triangle in front. How can I get away with that? So we know that the length of the trough is always 12. All right. So if we can know, well, that's always fixed at 12. So then what's happening here with this part, right? So this little area, as more water pours in, you know, the face of that triangular part that's just looking at the water, that triangle is getting larger and larger, but it's slowing down, right, as the water level goes up. Here's what we're going to do. Draw the face, the front face of our trough. And, you know, some things we can label with constants, other things are variables, right? So we know it's 3 across the top. We know it's 5 this direction. For the trough itself, the water, let's maybe put the water level right here. We know this is changing, it's H. There's also another distance that's changing, and that's this distance across the top. As the water level goes up, right, that distance gets wider and wider as it goes up and up and up, eventually getting to 3. I'm going to call this B, and I'm using B for a reason there. Think about this, right? That's a triangle, right? We're trying to figure out the volume of the water relating to its height. Well, if I want to get the volume of the water, if I can figure out the area of this triangle, the area of that triangle, I can multiply by the length of that base. The area here times the length, that will tell me the volume. So I'm labeling it B like it's the base of my triangle. Area of the water, for now, just right here, this area is 1/2 base times height. And harking back to a geometry formula for the area of a triangle, 1/2 base times height. Okay, well, all right, that's a start. But here's the thing. We really want that area just in terms of height. Right, once we have the area, we can multiply it by 12. That will tell us the volume. But we don't want 2 variables involved in that volume equation. We just need V and H. So looking back at our drawing again, can we figure out what B is in terms of H so that we can plug in here and get our area only in terms of H? And yes, we can. And it turns out because we know these other 2 lengths, the 3 and the 5, that will help us figure out a relationship even between the B and the H here in this drawing. So this is usually fun to do in a classroom. You know, we're all looking at this drawing and I can say, okay, you know, think back to anything that you ever learned in math. What concept would help us get an equation that involves all 4 of these, B, H, 3, and 5? Usually takes a few minutes, but someone eventually realizes, hey, these are similar triangles. This little triangle here is similar to the big one. Its sides are in the same proportions. And yep, so, you know, there's different ways we could set it up, but one way would be to say B over 3 is equal to H over 5. You could do different things, but it's all going to work out to be equivalent. If B over 3 is equal to H over 5, then we can multiply the 3 over, and we realize B equals 3/5 times H. And that we can plug in for the B here. So our area is 1/2 times 3/5 H times H. our area is, what's that going to be? 3/10h squared. Area of this triangle here. Of course, it's not the area that we really want. What we want is volume. But if I know the area, all I got to do is multiply it by 12. Volume equals 12 times area, let's say. So if I multiply these, 12 times 3/10, let's see. Well, the 12 and the 10 would both reduce by 2. So that'd be 6 times 3 is 18/5h squared. And I did it. We got the volume of the water just in terms of the height. Took a lot of work, took some clever thinking, similar triangles, you know, saying, hey, I need volume. Let's instead just focus on area, you know, and then, but we got it. Okay, once we have the equation relating volume and height, I'll say, all right, time for derivatives. And this is almost like the easy part, right? So derivative with respect to t, dv/dt equals derivative here, multiply the 2 down, 36/5h times dh/dt. Now we got to think, okay. In our derivative equation now, which of these rates, which are they asking about? So if you go back to the original question, how fast is the water level rising? Well, that's talking about the rate of change in the height. So it's the dh/dt that we're trying to figure out. Well, what does that mean for dv/dt? And what does that mean for h? And it turns out they told us both of these just flat out, no work at all. They told us that water is being pumped in at 2 feet cubed per minute. So we know the volume is changing at 2 feet cubed per minute. And they told us to do it at the moment that the depth of water was 1 foot. So 2 equals 36/5 times 1 times dh/dt. Let's see. What's dh/dt gonna equal? Let's see, if we multiply by 5, that's 10, divide by 36, 10/36 would be 5/18. Like that. 5/18, what are the units? Units of height, units of time, units of height were feet. Time here was minutes. 5/8 feet per minute. The decimal equivalent isn't so pretty. I'm going to leave it as 5/18 feet per minute at that moment. Very cool. All right, part B. What was part B? If water level is rising at 3/8 feet per minute, when depth is 2 feet, how fast is water being pumped in? Ooh, okay, switching things up. The water level is rising at 3/8 feet per minute. So that's telling us the change in the height. When the depth is 2 feet, okay, that's what h would equal. How fast is the water being pumped in? How fast the water is being pumped in is the dv/dt. So here, what's nice is we already know our equation. We already know, see, where's our derivative equation? dv, oh, it's back up at the top of my page. dv over dt equals 36 over 5h dh over dt. But now this time we're looking for the change in the volume. Okay, cool. We can plug in h, we can plug in dh over dt. When the depth is 2, rate of change of height is 3/8, and we can do it. How fast is water being pumped in? 36 over 5 times 2 times 3/8. I'm going to go with the fraction 27 over 5. When I do all that, what are the units? Units of volume divided by units of time. Volume, that's feet cubed per minute. Right, think about that. The water level's rising at 3/8 feet. That's pretty slow, right? Not even half a foot in a minute. And it's currently 2 feet deep. So, right, so because of our trough and its dimensions, right, we can tell exactly how fast water is being pumped in if we notice those other things happening. That's pretty cool. That's pretty cool. 27 over 5. What is that as a decimal? 5.4 feet cubed per minute. About 5.5 feet cubed of water. Trying to imagine what that would look like. Anyway, we got it. That is it. Well, that was a big question. That's it for 3.9. Check out homework.